Now we will discuss the constraints which are called octagonal constraints. In the octagonal constraints, we are also allowed to write bounds on sum of two variables and subtraction of two variables. Or we may be looking for a solution for integer or rational numbers. So consider conjunction of octagonal atoms F for variables x1 to xn. To solve this, we will translate the problem into a difference logic constraint, and we introduce the variable to x1 to xn, x to n. There will be twice as many variables in our encoding, and if there will be a encoded difference logic constraint formula has a solution, then we will have a solution from the original problem. So let's see how do we going to translate our constraints. Before that, we need to understand the role of these new variables. So for us, we will use 2i minus 1th variable to represent the variable xi, and the 2ith variable to represent minus xi. Slightly confusing idea, but once you see the encoding, you will understand what is going on. So let's suppose I give you constraint xi less than equal to b. How do I encode it? I will say that its positive representation minus its negative representation, that means twice the value, is less than equal to 2b. Okay, that's pretty simple. Now the other thing is minus xi. How do I encode minus xi? Just swap the rows, and then you saying that less than equal to 2b. If I say I minus xj, it introduces two constraints. It says that a positive representation of xi minus the positive representation of xj less than equal to b, and the negative representation of jth minus or negative representation of ith variable is also less than equal to b. The sign variable sign is exchanged. Similarly, I define xi plus xj minus xi minus xj, and this gives us the encoding into a difference logic constraint, because all the constraints here are subtraction. One variable is subtracting another variable, and there is no bounds on the constant value. You can easily check that if you have a satisfying assignment here, you can construct assignment here, and if there's a satisfying assignment here, you can construct it here. So here is, you can easily check if you have assignment in the original formula, the assignment of the encoding. You can see that you can simply write vi minus vi, v1 minus v1, v2 minus v2, so on, will be the satisfying assignment of f prime. Now let's suppose you have a satisfying assignment from the f prime formula. How do I construct the satisfying assignment of the f? So what do? You basically take the positive representation, take the negative representation, subtract them, and divide by 2. Their average will satisfy the original formula. It's not very difficult to see why that may be true. You can easily see that So what we can do when we encode into f prime and we got this constraint with twice as many variables, you can turn into dBms, and which we will call octagonal dBm. So let's see how they look like. So let's suppose you have a formula which has only two variables, and once we encode them x1 to x1 x2, then we will get a x1 x2 x3 x4 in our encoding. I have dropped the prime such that we don't need to write a prime repeatedly. So let's suppose x1 goes to x1, it's positive representation, x2 goes to x4 as its negative representation. That means it becomes x1 minus x1, and x3 is the positive negative representation of x2, and x2 is the positive representation, negative representation of x1, and then you write x3 minus x2, that is also less than equal to 4. So there, if you write them down, it comes like 4 and 4 these positions. Similarly, x2 minus x1 gets encoded like these constraints, and if you write them, you get 5 and 5. And similarly, you keep writing them, you find these entries showing up. So understand that we introduce a notation of this bar. If I give you an even number, I will tell you an odd number before that. Yeah, that will give you the bar. And the bar is applied on an odd number, then it will tell you the even number afterwards. For example, bar of 3 gives you the even number next, so that is 4. And the bar of 4 gives you back 3. Okay. So 1 1 gives you 2 2 because they both are even odd numbers, and their bar is the next even number, and that is 2 2. 2 1, you can easily see that the bar of 2 gives you 1, bar of 1 gives you 2. Old octagonal DBM is coherent if the pair ij and ji bar is equal. Okay, so you can look at easily. Okay, so this is column 1 and row 4. Okay, so you can say that it's a 4 1. Okay, so then you just put the 1 4 bar, which is basically 2 and 3. So 2 second row, third column, and which is the center. How do we check unsatisfiability in rational space? We construct an ODBMs and run our standard algorithm, and for 2n, because there are 2n variables, it will take 2n steps. If you have 0 entries in the diagonal, they have a SAT, otherwise you don't have a satisfiable formula. However, this method does not work for integers, and you need to interpret your ODBMs differently, and then that will be covered shortly.